Welcome to the Explainer. You know, everything that moves, from planets way out in space to the phone right there in your hand, it all follows a hidden set of rules. Today, we're going to pull back the curtain on those fundamental laws of motion. Let's get right into it.
I mean, seriously, think about it. Motion is absolutely everywhere. You see leaves fluttering down from trees, water rushing over a dam. Even when you're totally still, you've got blood flowing through your veins. But for something so common, it actually took humanity centuries to finally figure out the simple, beautiful laws that describe it all.
Okay, let's dive in. Before we can even begin to understand the why of motion, we need to get on the same page. We need a clear, precise language to describe the what. And that means we have to get really specific about some words we probably throw around every day.
First up, velocity. Now listen, this is not just about how fast you're going. That's speed. Velocity is a little more specific. It's about how quickly your position is changing and in what direction. So, a car going 60 miles per hour heading north has a totally different velocity than a car going 60 miles per hour heading south. Direction matters.
And it's so important to get the difference between your velocity right now versus your velocity over an entire trip. What you see on your car's speedometer, that's your instantaneous velocity. But let's say you drive 120 miles and it takes you 2 hours. While your average velocity was 60 miles per hour, even if you stopped for coffee or got stuck in traffic. See? They tell two completely different stories about your journey.
Now here's where things get really interesting. Acceleration. We usually think of this as just, hitting the gas, speeding up. But in physics, acceleration is any change in velocity. That means speeding up, sure, but also slowing down. And get this, even making a turn at a constant speed is acceleration because your direction is changing. Wild, right? So we've got the language down. Now how about we try to visualize the story of something moving? Turns out the best way to do that is with some simple graphs that can turn all these ideas into a picture that actually makes sense.
Think of it like this. If you were to plot your position against time on a graph, the steepness of that line, what we call the slope, at any single point tells you your velocity at that exact moment. So, a really steep line means you're moving fast. If that line flattens out and becomes horizontal, well, you've stopped.
So here's the really crucial part. A changing slope must mean a changing velocity. And what is a change in velocity? It's acceleration. That's the definition. So a straight, sloped line means you're cruising at a constant velocity. But the second that line starts to curve, you know for sure that acceleration has just entered the chat.
And check this out. Here's a brilliant little trick for reading these graphs. If the curve bends upwards, kind of like a happy face, that means the object has positive acceleration. If it curves downwards, like a sad face, it has negative acceleration. It's a super quick visual shortcut that tells you exactly what's going on.
Okay, so now we can describe motion pretty well. But here's a crazy thought. For nearly 2,000 years, humanity was completely and totally wrong about what actually causes it. What seems so obvious was actually our everyday experience tricking us. So, the great thinker Aristotle argued that you need a constant force to keep something moving. And that feels right, doesn't it? If you stop pushing a box, it stops moving. But then Galileo came along and realized that's only because of friction. He imagined a world without friction and discovered something profound. Motion doesn't need a cause to continue, it only needs a cause to change.
And this key idea is called inertia. It's basically the natural tendency of an object to just keep on doing what it's already doing. You could almost say objects are a little bit lazy. They don't want to change their state of motion unless some outside force comes along and makes them. That's the real default state of the universe. Building on Galileo's incredible work, Isaac Newton gave us his 3 laws of motion. And the first law? It's pretty much the law of inertia. It tells us that objects are stubborn. An object at rest, like a soccer ball in the grass, is going to stay at rest. An object in motion, like an asteroid flying through deep space, is going to keep moving in a straight line at a constant speed forever. That is, unless an outside force, like someone's foot or a planet's gravity, gets involved.
So what happens when a force does act on an object? Well, that's Newton's second law. It gives us that world-famous equation, F equals ma. It's a simple but incredibly powerful relationship. The more force you apply, the more it accelerates. But its mass, how much stuff it's made of, resists that acceleration. And that's exactly why it's way easier to get a bicycle moving than it is to get a whole freight train moving. And finally, the third law. This one reveals a deep, beautiful symmetry in the universe. For every action, there's an equal and opposite reaction. Forces never happen alone. They're always a two-way street. When you push on a wall,
That wall is pushing back on you with the exact same amount of force. It's how rockets work. The rocket pushes hot gas down, and the gas pushes the rocket up. Every single interaction is a perfect partnership.
Okay, that's all great, but how do these three simple, elegant laws explain the more complex kinds of motion we see every single day, like the perfect arc of a thrown ball?
Well, one of the most powerful tricks in all of physics is just to simplify a big, complex problem. And for projectiles, we do that by splitting the motion into two separate, one-dimensional problems. What's happening horizontally and what's happening vertically. The absolute key here is to realize that these two motions are completely independent of each other.
Think about it. In the horizontal direction, once the ball leaves your hand, there's really no force acting on it, so its horizontal velocity is constant. It just coasts along at a nice, steady speed. But in the vertical world, oh man, it's in a constant battle with gravity, which pulls it downward with a constant acceleration. It's basically just in free fall, like any other dropped object.
And here's the magic. When you combine those two simple, independent motions, the constant coasting forward and the constant acceleration downward, what you get is the elegant, predictable arc of a parabola. Every single time. It's not a mystery at all. It's just the laws of motion playing out right in front of our eyes. And that's really the beauty of it all, isn't it? These few fundamental rules, discovered centuries ago, don't just describe a ball being thrown here on Earth. They describe the orbits of planets, the paths of entire galaxies, the very structure of our universe. And it just makes you wonder, what other incredible secrets are they waiting to unlock?